Good morning. I'm Boris Shingarov, and my day job at LabWare is writing virtual machines, and including native code generation backends for virtual machines. And before I show you what I did with gem5 and how gem5 helped me, let's talk about some background. So around some late 1960s, Alan Kay and Dan Engels and some others at Xerox Palo Alto Research Center started a project called Smalltalk. And that went through a number of intermediate generations of their system. So they had, this is Smalltalk. They started around 1968, and they had the system Smalltalk 71 and 72 and 76, and the standard gold reference is Smalltalk 80, and this is still ongoing with a very active research community. There's several of them. One of interesting ones is something called Faro, a team at INRIA. In fact, I was just last week presenting at their conference called ESAG, the European Smalltalk Users Group. And they are doing some quite interesting work. What this is coming from is interesting because this is a descendant of the Simula language, and the direct descendants of these ideas are languages such as Java, Ruby, and a lot of others are basically directly taking the way how this works directly from Smalltalk. The idea there is they have what they do is it's a simulation of objects, which are active entities that send messages to each other. And this has pretty much revolutionized the way how we write software. But a practical limitation of this nice way of doing software is speed. The simulation was very slow. Until in 1983, Peter Deutsch and Alan Schiffman introduced dynamic or just-in-time compilation, where you compile the byte-coded simulation script into native machine instructions on the fly. And later, people added other interesting optimizations. So you've got optimizations of this just-in-time. You've got polymorphic inline caches, picks. You've got native stack mapping, and many others. Better garbage collection algorithms and some other interesting optimizations. So when you work in the area researching, trying to improve these optimizations for other languages, you keep in mind that what makes it fascinating still in 2017 is how the simulation itself is reflected in the simulated world. So the objects that are simulated and exists in the simulated universe, they know about the computational mechanisms of that lead to the simulation. So you've got this picture that at the very bottom you have the simulation engine, or the virtual machine, right? And then you've got the base image. This is the VM world, and this is the virtual image world. And you've got the base image, which is your base class library, essentially. And then you've got tools such as debuggers, inspectors, and so on, code browsers, code editors, and then there's application code. And this is all homogeneous. Really, there is no difference. But you cannot see into the details of optimizations of the VM because things like the stack mapping is completely transparent. So on the plus side, you're virtually unlimited in how you perceive what's going on in the software, which is key to new discovery. The Smalltalk simulation gives you tremendous power. Objects are malleable. You can change them. You can stop the simulation and change your objects, and you can programmatically send messages inside the debugger or inside the inspector, however you want, at whatever time you want in the middle of execution, etc. The limitation of this picture is that because this is a live system, you have to be very careful. If you screw up anything here or anything here, which you can do from within the simulation, you now cannot debug it because your debugger is itself based on this mechanism. The debugger itself lives inside the simulated universe. So debugging the VM or any of those optimizations with that debugger is in the classical, in this classical picture is totally out of reach. So when I sat down to work on a better JIT compiler, this was not useful. So I wanted to change the JIT in two fundamental ways. The project was about two things. Well, one, I wanted automatic retargetability or target agnosticism at the VM engineer level. That I wanted to base on processor description languages, PDLs such as ArchC and so on. And that idea is not new. Basically, what you have is you take a PDL, which is a formal description of your processor, and it doesn't matter what it is. I used different architectures such as ARM and PowerPC and MIPS. And recently I tried, and that works quite nicely with RISC-V. And you take this and you feed it into this JIT synthesizer. So this is synthesizer. And it spits out a native compiler backend. So you've got a native compiler. And because all of this is happening here in the simulated world, all of these inspectors and debuggers, they give you a tremendous insight into what is happening inside this, this synthesizer. But that's not good enough. We'd like to use this technology to build critical systems where human life depends on our software. So the idea here is that usually programmers reason just in their heads. What gets written down is the actual computer code. And the justification why the programmer thinks that his code works is at the very best maybe put in a comment, but typically you just left it to deciphering what they meant. And the validation argument about, well, how do I really how do I argue that my code is correct is through testing. That you throw a bunch of tests at it and it appears to work, and you say, oh, okay, I'm done. Well, where human life critically depends on what you write, this is not good at all. So instead what we do is we do verification based on formal proofs. And when we program this critical software, we don't program the manipulation of data, or we don't program what the program is going to be doing. Instead, we use the idea of David Hilbert that proof is itself a mathematical object about which that program that we write, that program is going to be manipulating the actual proof. And the final program is going to be automatically extracted from the proof thanks to something called the Curie-Howard correspondence, which I will not get into details now. Okay, so this is great, but when you work with proofs manually, or even in some sort of proof assistance such as New Perl or ACL2 or Coq, with something as complex as a JIT compiler, the complexity quickly becomes prohibitive and totally unmanageable. So it's just hopeless to just do it in the normal way. So what you want to do is to bring these proof objects into the Smalltalk simulation. So this is what I wanted to achieve. And with this classical debugger, it is not possible because you are changing the VM on the fly, and when it doesn't work, your debugger doesn't work. Is there anything better? Well, one alternative approach is what Java does, is the debug-wire protocol. But that's still, if you screw the base image, it's fine, but the VM itself is still screw the VM up and hope to debug it. So instead, here's what I did. So you have this system, and this is the mother system. And then inside gem5, you have gem5 running another VM inside with the full stack of things. And from this debugger, which is now remote enabled, you talk to the debug port on gem5. And what happens is that you map from the structure of this VM to the structure of the simulated VM, which is, remember, these are optimizations of things that are already known to the whole simulated system. So back in the days of Symix, we had simulations where you, for example, port Linux to a chip that's not there yet. What you do is you debug on the simulated chip, affording early feedback. So with a VM, the traditional approach means months or years before you have the first feedback, because you have to have all of these different pieces. You have the JIT, you need to have the stack, you need to have the memory allocator, you need to have the garbage collector, and so on. Now, people ask me, well, but this is all software, right? So you're just replacing software with simulating software. So how is it gaining? Well, the point is, before you sit down to implement an optimization like JIT or stack mapping, the concept in question is already exists here in simulated form. It's just very, very slow. And because all of this is mapped to the structures in gem5, you can use this mapping between the virtualized gem5 VM and the real VM. And when you have something which is not implemented, for example, if you don't have a garbage collector or you don't have your memory manager at all, we haven't started writing it yet, you trap on a magic instruction, and you get a callback into the outer or mother debugger, and you use the simulated slow mechanism because it's mapped. And then when the function, which was not implemented in the actual system, finishes running in the simulation, you get back and continue from that point in the gem5 simulation. And this is how you achieve very, very fast turnaround or very fast feedback. You can, if you have a part of JIT and you wanna do integration testing, you can, even though you have none of these other components. So this is how we were able to write a totally new JIT and a totally new stack mapping and so on within a very fast time frame, which would be completely impossible if we were not using gem5 simulation.